Okay, we're looking at workbook problem 31.7. This example, let me hit pause over here real quick. And just to show you what's going on here, if you recall this demo from a while back, we have this ring on here. We can make this thing levitate on here. Basic physics here is this is a solenoid, it's connected to AC power, and as a result we're getting an induced flux up, then an induced flux down. So this ring is experiencing a change in flux up, then a change in flux down, and as a result that induces a voltage in the ring itself, which is also oscillating. So we have an AC voltage source induced in this ring. Okay, that's what we're going to try and understand. Now, you might notice there's no capacitance here, right? Well, what does this mean and why is this problem here? So a model of this problem might look like what you see on the board here. We're going to have an AC source. In the problem, it tells us, let's call V naught E for some reason, I guess for induced EMF, right? And we see we've got some resistance and some inductance. You might say this problem is going to be easy. I'm just going to set C equal to 0 and all my problems will work out. That is actually bad. It turns out I want you to think instead of setting C to 0, I want you to set X sub C to 0. The capacitive reactance, the amount of ohms associated with the capacitance goes to 0. Why is that? Well, X sub C is equal to 1 over omega C. If we set C to 0, it's like, oh, what does this mean? Is that infinite? It doesn't make sense. All right. So we don't want to set C to 0. We want to set the capacitive reactance X sub C to 0. Well, at this point, the problem is actually pretty straightforward. I think in part A, we're supposed to get the impedance. Well, we know the impedance is the square root of R squared plus X sub L minus X sub C quantity squared. At this point, I know XC goes to 0, XL is omega L, so this is a simple one. We get that formula. Now, I'm actually going to do the next two parts out of order just because you'll see why in a second. I'm actually going to skip to part C. If I want to get the phase angle, that's tangent inverse of XL minus XC all over the resistance. I'm using the formulas on the back of the book, okay? Well, in this case, phi is equal to tan inverse of omega L divided by the resistance. That's it. Now I'm going to go back and do part B. You might be saying, why didn't you do part B first? Well, I'm looking for the current. Well, the current requires two things, right? We need the current amplitude first. The current amplitude we could have gotten right away. I max is equal to V of the source divided by Z. Well, in this case, the V of the source, we said, was the EMF, and Z was this function down here. All right, so far so good. Well, current is current as a function of time. That's going to equal I max times sine of omega t minus the phase angle. And since we need the phase angle to understand current as a function of time, I figured I'd do that part first. So in this case, out of all that, we get now, in this case, I'm going to leave phi like that, I guess. If we had a number, we could plug it in, or I could write that in there, and it's just a big, ugly mess, so I apologize. I'm just going to leave it at that. So that's part B, I believe. I'm just going to check the question, see where I'm at. All right. Cool. That's what we're talking about. So in part D, we're given some numerical values. I think we're told R equals 60 microohms. L is 400 nano. Microohms, nanohenries. And then we see this mysterious number 60 hertz. All right. Well, I can tell by the units, this is F. Now my question is, should it be F or F naught? Well, in this case, that's the frequency we're operating. Operating frequency is F. Another way you could tell this, look, without any capacitance, there's no resonance. The capacitance only happens when X sub L equals XC. If XC equals 0, there is no resonance. So this circuit, basically, we expect at high frequencies, the inductor is going to lock down. This is a purely, well, it's not purely inductive, but we expect the inductor is going to lock down the current flow at high frequencies. It's going to allow current flow at low frequencies. So, all right, that's good. This is F naught. So keep in mind, the units are what told me it was F. So if I need omega, omega would be 2 pi times F. At this point, I hope you agree. Oh, wait, there's one other piece of information. We're told the current peaks at 1 kiloamp. Well, the peak current is the same thing as the current amplitude or the max. So this is I max. At this point, we know some numbers. If I know this, 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 and this, I should be able to solve for that. And I think you could do that. All right. You could check in the solutions as well. What's the next part? Plot Z versus F. And it gives us some numbers. Plot current amplitude versus F. So to be clear, let's go actually look at these plots. Let me do a share screen because I have the plots already made up. You should actually make them and verify that you can do this. What chapter is this? 31. And where were we? 31.7. That's 31.6. Is it this one? 31.7. There we go. All right, so you got these solutions. You can read them. There's the numbers when we plug this all in. So what I did is I made an Excel table. I got L, I have R, and so I tabulated the frequency. And remember, to get Z, you've got to use omega. So you're going to have to figure out the Excel formula used to get that. All right. Now in this case, oh, and notice the units, microohms, kilo. Yeah, so you're going to have some work to do. If you have trouble making these kinds of plots, there's no shame in making a column of Z in ohms and then doing the conversion to microohms. You could also do one that has I in amps and then do the conversion to kiloamps afterwards, right? You could also do phi in radians and then convert to degrees at the end. The idea is Excel uses radians. Our calculations use radians, but human beings think in degrees. So if we want to, we could go look at these plots. What happens? The impedance increases, okay? The impedance starts out at 60. Well, remember the resistance was 60. And then as we increase the frequency, we have an impedance of almost 3 times that. So remember, in general, the formula for this was Z was equal to, I think it was R squared plus omega squared L squared, right? So it's a parabola. Well, no, it's its own thing. Let's not try to name it. Let's avoid trying to categorize things. All right. Anyways, so the impedance goes up. All right, that makes sense. As you increase the frequency, the inductor is going to put things on lock. Notice what happens to the current amplitude. All right, the current amplitude, maybe if I make this just a little bit smaller, we could see both of these at the same time. Notice they do kind of opposite things. Well, why is that? Remember, this is not current. This is not current as a function of time. Current as a function of time is a sine wave. This is I as a function of time, right? What are we plotting? We're plotting current amplitude as you change frequencies. If you use different frequencies, the inductor will have more or less of an effect. So remember, I max is equal to V naught divided by Z. So it should be the opposite of this formula, right? If Z increases, the current amplitude goes down. We get less light out of our light bulbs when we're not, when we operate at high frequencies, and the inductor locks things down. Finally, let's look at the phase angle. Well, if you operate this thing with a battery, right? Operating it with a battery is like zero frequency. So this, believe it or not, this is essentially like operating with a battery. Or if F equals 0, you could think of that as a DC circuit. Well, if it's DC, we don't expect any phase angle. The inductor, nothing's changing. The inductor is not going to react. The inductor is basically not in the circuit. It's just a resistor. So everything would be in phase. As you go to higher and higher frequencies, right? What does the phase triangle look like? We've got resistance here. We've got X sub L. We don't have XC. We've got the total impedance is this side. And we know our phase angle. Well, you can see here as in the inductive reactance increases with increasing frequency. So as F increases, as F goes up, omega goes up, and X sub L also goes up, and that's why the phase angle goes up. Remember, if it helps, phi is equal to tan inverse. For this problem, since there's no X sub C, it's tan inverse of XL over R for this problem. So in this case, it makes sense that the phase angle keeps creeping up. You start out with no inductive reactance at zero frequency in DC, and then you gradually increase it. Sorry, it's been a long day. This is like take 3 or something on this one. All right. And I think that's all we have for this one. Let me make sure. All right, so yes, that's all we have for this example. So what are the things that we're supposed to learn about this? If you're missing a capacitor in the circuit, instead of setting C to 0, set the capacitive reactance to 0. Then the rest of the problem can still work the same as normal. In this particular example, with XC gone, we could only get positive phase angles, right? So the current, yeah, you could model this. And we see that there's a difference. One of the main things I hope you take away from this problem is there's a difference between current versus time plot and I max versus omega plot. The idea is the current as a function of time keeps flipping like this. And this max level is the amplitude. And the idea is if you use different frequencies, if you operate at different values of omega, you get different values of this. And so we saw in this case, the current would kind of fall off, right? And I think it started doing this kind of shape. It starts drifting towards 0. So again, choosing your frequency will affect the amplitude of this sine wave.